All right, let's take a look at example number 3 for Hess's law. And just like the previous examples, we're given a target equation as well as 3 reference equations that we need to use to find the delta H of this target equation. Now, just like we did in the previous examples, I'm going to compare each reference equation with the target equation to see what I can do to change these reference equations, right? So the first thing in the first reference equation is calcium, and that is common between the reference and the target. The coefficient is the same, as well as they're on the correct side of the arrow. So according to that, it seems that I don't need to change the reference equation at all. Moving on to the next one, I've got 2 carbons in my reference equation and 1 carbon in my target equation. The coefficients are different, but the positioning of it is correct. Now, if I'm looking according to the calcium, it seems as if I would leave my reference equation as is, whereas if I'm comparing it based off the carbon, I might have to make some alterations, right? So because there's conflicting possibilities, I'm going to maybe stop and not decide what to do with reference equation number 1 until I take a look at the next 2. Okay, so let's take a look at reference equation number 2. I've got CO2 gas produces carbon solid plus O2 gas. Now, O2 seems to be the only commonality between the reference and the target, as well as the carbon as here as well. So this kind of decides for me what to do with reference number 1, right? So if I take a look here, I have 2 carbons on the left side. And then if I leave this equation as is, this 2 and this 1 would mean that one of those carbons would cancel out, right? So I'm going to decide to leave the first one as is, right? And I'm going to leave the second one as is as well. So times 1. Now, the only thing that you might wonder is within regards to O2 here, right? So why is it that we've left it even though the coefficients are different? That has to do with the next equation. So if I take a look at the next one, I have CaCO3, which is here and here, right? And this seems to be on the opposite side. I've got CO2 that's not in the target equation, and I've got 5/2 O2, right? So I have this oxygen here, whereas I have 3/2 oxygen on the left side. So looking at these two, ignoring the coefficients for now, it would benefit me if I flip this over so that I can get the CaCO3 on the same side as well as the O2 on the same side, right? So what I think I'm going to do is multiply this by -1. That just means that I'm going to flip that reaction, right? As usual, I'm going to check by writing out these reactions and see if they result in the final target equation. And the first one, I didn't need to make a change for that. Oops. For the second one, I also decided that I didn't need to make a change for that. Now, a lot of these questions are going to be trial and error, right? So as you see, I decided that I'm going to try and do multiply this by 1, but if you wanted to try something else, you can. You might get used to, after you write it out, you might see that that might need to change, right? So it's not something that you maybe get right away. You might have to play around with these reactions a little so that they can end up as the target equation. For the next one, we decided that we would flip that. So 5/2 O2 plus CaC2 CO2 plus CaCO3. Okay, so let's see what things cancel out. So as I mentioned earlier, I've got 2 carbon here, but only 1 carbon here. So I think I can cancel this out. So this goes away. And then I'm going to erase that too. So there's one carbon left over there. CaC2, I've got one CaC2 over here and another over here. I've got one CO2 gas over here. I've got another CO2 gas here. Now, when it comes to the oxygens, if you take a look, I've got 5/2 oxygens here and 1 oxygen here. So 5/2, if you're looking at it for decimals, that might be easier, is 2.5. If I've got 2.5 here and 1 here, if I cancel this out, this is going to give me 1.5, which is 3/2. Okay, and I think that's as much as I can cancel. So let me just write out the reaction. So Ca gas plus carbon solid plus 3/2 O2 gas. And if you want to write that as a decimal, that's totally fine if you prefer to do that. And all of this forms CaCO3 solid, right? So you can see how that did result in the target equation. Now, it doesn't necessarily, you don't necessarily get the right answer right away, right? So it might be helpful for you to maybe try one thing and then look back and see how else you can change that. The only thing that I would recommend is for you to make sure that you leave your delta H numbers until the end, right? Until you get your target value, don't mess with the numbers. Once you have that, you can use those to then add it, right? So I now figured out that this is the correct target equation and these are the different variations. This is how I have to change these reference equations. So I'm going to write my delta H values and then add it up to get my answer. So delta H for the first one, I didn't change. So I'm going to write that as is, negative 62.8 kilojoules per mole. The second one also I did not change, so delta H is equal to 394 kilojoules per mole. Oops. And the third one, I did change. I flipped it over, so the sign of that will change. So it was positive, it will become negative 1538 kilojoules per mole. Just make sure that's obvious. And then I'm going to write a positive there. Okay. And if I add all of these numbers up, I should get the delta H value for this target equation. The answer comes out to become negative 1206.8 kilojoules per mole. But as you remember from sig figs, when I'm adding up a bunch of numbers, the answer will always have the lowest number of decimal places of all the numbers that have been added, right? So both reference reaction number 2 and 3 have no decimal places, they're whole numbers, which means my answer is also going to be in whole numbers. So it's going to be negative 1207 kilojoules per mole. So that is my final answer here. So this is probably the most complicated of the examples that we've done so far. But again, it might take a few turns for you to maybe figure out what changes to make to those reference equations. But if you follow these sort of steps, you should get to that correct answer.